you for the introduction. And hello everyone. Today I am going to talk about towards a deterministic Ethernet networking solution for software-defined vehicles. This work is actually a collaboration work with our engineering research, and we are going to share with you our experience. We are not saying that this is a total solution of the network, but we are moving towards that direction. Just before our keynote speaker, Dr. Shazzad, talk about that the software is very important. The software complexity is very high. And we are moving towards a direction which is software-defined vehicle. And when we look into this and we find the definition, what is actually software-defined vehicle, there are many different definitions we can find. Different group of people actually sees it in different angles. To me, I think I can simply say that it is a vehicle which can deliver continuous, improved and dynamic experience to the customers. What it means actually. For instance, we can say that the customer will experience his car behavior is changing over the time. We can think about it that the experience customer is seeing in Halloween may be different than actually in Christmas. So this is a very high level. But towards going toward the software-defined vehicle is not actually a simple and not short work. What it brings a lot of changes in the actually our electrical architecture, software architectures, and also the communication. In fact, so couple of things, the enabling things which can be needed for software-defined vehicles. One of the most important things is the decoupling of the software and hardware, which previous speaker already emphasized that. And these we can say, okay, the total separation and total decoupling cannot be possible. But yeah, as much as we can. And this eventually, or maybe consequently actually, impacting our electrical architecture and software architectures. And current architecture, which is being all OEMs, most of them utilizing like domain-based architecture or common gateway architectures, cannot support that. We need to move towards something. And where we are moving that is central computing architecture, where we are consolidating the ECUs, or in another sense, the computing to central computing. And this in our electrical architecture side. But we also need service-oriented communication instead of signal-based communication, which is we currently almost everyone utilize. And definitely we are here for Ethernet conference, and the dominant communication technology we need to move towards actually the Ethernet. But what values is actually the, I actually put a couple of very simple one, that on-demand features, fast and frequent updates, in-market enhancement. But in my opinion, it is enabling software-defined vehicle enable us to move forward the intelligent transport system. I remember in my early young age, I used to watch a drama series that called Night Rider. So maybe this is the beginning to take us towards that. But you know, it comes with challenges, especially on the internet side or the networking side, I would say. As we move toward the central computing, most of the compute is going to be occurred in the central compute. And the data from the sensor needs to go to the central computer, it needs to be processed, and then it will go to, again, the command it created, go to the actuator. This is actually becoming a longer path than current one. So, the end-to-end latency will be increased. And we know that our safety critical applications are required different type of mixed criticality here. So these, but also we require low latency but also bounded for the real-time application. So there are some actually very stringent challenges are there. And on top of that, the safe operation, we need reliability in communication. So it adds more complexity into the system. So these challenges we need to address. But when we need to address these challenges, we have to set out some of the goals also for our design. We set out some of the goals, and that goals is actually, I will say, that aligned with what our keynote speaker actually says, and we also think that a similar way, that we have to utilize the standardized technologies. This is one of the reasons for all of these actually goals. The implicit goals is to actually the cost-effective system design and multi-vendor solution for that technologies. And it actually, why we need for interoperability? Because interoperability is very essential. We don't want to be bounded with some one supplier, and there should be interoperable because the changes happens and changes will happen. That is the constant. Okay. And complexity, we need to reduce the complexity as much as possible. So our motto is keep it simple. And here I put it that the scalability in design, but I would like to say that not only the scalability, we need the actual elasticity. Because a solution needs to be applicable for all the actually our programs, all model years, all the teams, and we just need to change it, maybe some configuration. And that is actually another part of the actually discussion or talk, but we need this elasticity in the design. So in order to meet this goal and to address those challenges, where we are going to do that for the Ethernet. And IEEE is actually the goal source for Ethernet. And TSN is created for that purpose. So we are going to explore TSN standards. But TSN standard is not a single standard. It is an umbrella of standards. These umbrella of standards can be categorized in 4 different areas. One, time synchronization, latency management, traffic policing, and reliability. Time synchronization is part and parcel of the in-vehicle network. Without it, we cannot synchronize timing and many different network nodes, also in distributed software in different ECUs, or we can say the different ports or compute environments. 802.AS in 2020 is the latest, we know the latest time synchronization standard, which also include a profile for the automotive standard, automotive use cases. So we need to move into it. Okay. I'm not going to define all of those, describe all of these things, but I'm just giving a perspective that what we explore and what we actually do. Traffic policy, we require it to filter traffic because of some bandwidth allocation or bandwidth management, or sometimes also the network security. PSFP, for stream filtering and policing, which is 802.1 QCI, you can utilize it. As we said, the reliability is required in link communication. FRE are giving a good solution for link reliability. But the most important one, which we are going to focus on today, that is the latency management. Because bounded and low latency is the requirement, but we need also the regulation of latency for different applications. Application is getting more and more complex and more in numbers. So in latency management, it provided almost half dozen of techniques to be utilized, which we call the shapers. Like stick priority shapers, time-aware shapers, credit-based shapers, asynchronous traffic shapers, and CQF, which is cyclic and queue forwarding. Cyclic queuing and forwarding. So we would like to explore which one is the right tool for developer applications. And this is not a trivial task. So we have a couple of projects, we work on it, we explore it different ways, different studies, theoretical studies, analytical studies, and also simulation studies and experiments. So here, what is the right choice for our latency management? That is our goal. And as we say that time synchronization, ingress traffic policy, reliability, these are a whole subject, a big subject to be talked about. We are not going to focus on it. So how we come up with the selection of right shapers? Here I am going to provide some of the differences between the different types of shapers, which I just mentioned. Credit-based shapers is one of the shapers which is smoothing the traffic by de-bursting traffic. However, in some use cases, it does not guarantee the bounded latency. The upper bounded cannot be guaranteed. And it is actually per class level. That means there is 8 different classes in our IEEE 802.12 standards. It can be applied only for class level, not the stream level. Asynchronous traffic shaping, which is ATS, and GM is actually also contributed in this specification, RD. It guarantees bounded latency, and it can be applied in per stream filtering. So per stream shaping. So any stream can be shaped. But however, for some complexity reduction cases, a group of stream can be shaped together. And it has a burst control mechanism. So it has more control mechanism than credit-based shapers. And it can be, in some way, behaves if we configure properly, differently, in credit-based shapers also. Strict priority shapers is actually just providing the mechanism to queuing differently in priority base. So it is required definitely for any of the shapers we are going to use to prioritize the traffic. Time-aware shapers is required time synchronization. And time synchronization is very hard to achieve when the network is a little bit complicated. And if anything changes in the network or the traffic pattern, this time-aware shaper actually can behave very weirdly or maybe broken sometimes. But it has very fantastic characteristic. That is that it provides lowest possible latency and jitter for scheduled periodic traffic. So if we require that, in some cases, yeah, these options are available in the toolbox. Cyclic queuing and forwarding is good for long many hops networking, which is maybe industrial. I am not sure anyone is currently or explore the CQF for automotive use cases. But it is also required time synchronization, which is a little bit hard to attain or to keep attaining. So looking into this, we can say that, okay, maybe CBS is a good choice, but it is a limited control. So maybe we can go to the best solution for the ATS. And we actually explored all of them, means ATS, CBS, and stick priority shaper, not the CQF. But we are here, we would like to actually discuss with a simplified topology that how we think that the ATS can be good, best choice. Okay? Delve into that. This is a very simplified topology. We know that the central topology. It is for our understanding of our principle, based on which we want to go to our solution. Here, in this experiment, we have three different critical limits of the traffic. Say, for example, high, mid, and etc. That is. And we actually make it the whole traffic such a way that it actually attain almost 70 to 80% of the link speed. And this percentage of the critical and mid-critical traffic is almost half of the actually the base of the traffic. So this is a simplified way. And we ran this experiment with SPS and with ATS with definitely still priority. Let's see one first thing, that only still priority shaping, what result we can get. Here we see that the high critical streams, which is the market plane, yeah, it satisfies latency requirement. But in the still priority shapers, the highest priority queue must be emptied when the next priority queue will be selected. So in this case, our medium critical priority latency requirement is not satisfied. So what we can do for that? We can utilize the ATS, because ATS has three different actually controls. One of them is committed information rate, another is committed burst size, and the maximum residence time. So using these three parameters, we can actually manipulate the stream's behavior. Here, one configuration, whatever it is, we experimented and we see that, okay, yeah, the latency requirement of medium critical streams is attained, but it impacted the high critical traffic adversely. So this configuration is not good, but we have control. We can make it. This is another one which is very much similar to the SPS. However, this is somewhat actually predictable, because if we make it, ATS configures such a way that it almost gives like SPS. Yes, we can control it. The last one, which configuration is actually allows us to meet all the needs. Here, we are satisfied with the critical latency also, and also the mid critical traffic also. So what we would like to actually, what message we would like to convey? That okay, with ATS, with the configuring with stick priority shapers, we can regulate the traffic per stream or per class or group of streams, such that our latency requirement, the bounded latency, can be satisfied. Sometimes the fast is not a good thing, because the software which is running there, which is receiving the frames, cannot handle the fast, so we have to regulate it. Okay, we need to if the earlier we have I remember I have an old fan in my home in early age, and they have very regulators. It has very few, very few actually configuration. Okay, we can go 1 or 2, but nowadays we know that we can control very efficiently and we can make it swiftly changing those controlling the fan or any other implements. So that regulation is required. So my thinking is that SPS alone cannot satisfy the latency goal. We need something else, and that is the ATS and the SPS enable fine tuning to satisfy our latency goals in the SDP. Thank you. I will welcome your questions.
And if you have questions, just feel free to come up to the mics.
Thank you very much for such an important topic. I'm Markus from Markus, looking at similar things. So I'm very curious. I have 2 questions. So for example, if the link, let's say the link from the core system to zone controller, you have a multiple stream with different critical. So you have to configure, so you apply different parameters for different stream, per stream direct shaper.
If I understand your question, that you were asking that different streams need different configuration.
Yes,
different configuration. And I did not mention it actually that when I am comparing CBS with ATS, that the complexity in configuration of ATS is more than CBS, but the value is there. Okay?
This is my second question.
Okay, and this is also depends on the implementation, and different vendors provided different numbers of actually filter possibilities. Also the groups, how many they step. We find that some of the actually the vendors have the capability of few actually group of skills they can support it. Okay, some.
Small thing, practical thing. When you separate them, do you determine how do you separate the traffic, or do you just define different streams? Let's say I have a safety traffic and I have a QM.
Yeah. So one of the things is the priority. Another thing is that is in the ATS that capability is that it has an internal priority also value, which in different hopes you can change the priority itself. So that cannot be possible in the CBS also.
Okay, thank you very much.
Further questions?
How sensitive is the performance to that tuning? If I have a vehicle that has a lot of configurability, its options are added, that work can change. Does each configuration some set of tuning? Does there need to be dynamic tuning, or is it stable enough that we make a lot of changes and then we're the same?
This is actually a very relevant and very important question, that how sensitive it is and how we can come up with actually this configuration. So this is, I would say currently, it is an open research question, okay? Because it depends on your topology, your traffic patterns, and also the link speed, all of these, number of things, okay? And then this, maybe we can work on it, that how it is, if there is any systematic way to find this like configuration parameters better, okay? But currently,